Okay, so today what we're doing is we're going back and refreshing ourselves on exponential functions and simplifying exponential expressions, excuse me. So we're going to look at both today. And everything I'm going to show you today, you did last year in accelerated coordinate algebra. Now, some of my ninth graders may not have seen some of the solving equations using like bases, but those are not hard, and you'll pick up on those pretty quickly. And I'm going to basically teach the same way I taught last year when we did them. All right, let's go over our warm-up, though. All this is 100% review, so we should be good with this. So this first expression is being squared, so I can square that. And we raise a power to a power, we multiply. Now I'm raising this negative, it's understood 1 to be to the 5th power, so it's going to remain negative. Power to a power, we're going to multiply, so we get x to the 10th, y to the 5th. Okay, all right. So now we are multiplying these two expressions, and when we multiply, we add the exponent. So a negative times a 16 gives us the negative 16. X squared times x to the 10th is x to the 12th. And y squared times y to the 5th is y to the 7th. So the simplified form of this expression is negative 16x squared y to the 7th. Okay? Number 2. All right, so we have this expression. There's some simplifying that can occur inside the parentheses, and then I'll deal with this exponent. Okay? So we have a fraction raised to a power here. I'm going to simplify inside here first. So if I see this, the a is raised to the negative 2nd power. And when we have a negative power, what do?
Flip it.
Okay, you can think flip it, but that is what it's going to do. It's going to move it to the denominator. Now, the 3 is actually raised to an understood 1st power, so will it move? No, because this is really 3 times a to the negative 2nd times b to the 3rd. And even though we don't say the times, we know that they're actually all multiplied times each other. So the only part of this expression that's raised to a negative power is the a. So it moves down. All right, so what we have is 3b cubed over 2a squared, a to the 4th, b to the 5th. So there's a little more simplifying we can still do before we deal with this power outside here. We can say that 3 of these b's cancel with 3 of those, leaving 2. And a squared times a to the 4th is a to the 6th. So when I can't completely simplify this expression, I get 3 over 2a to the 6 b squared. Are we good? Now I can deal with the negative 5th power. The negative is going to take this entire fraction and we're going to flip it, so we'll have the reciprocal here. And then we'll raise everything to the 5th power. So 2 gets raised to the 5th, and 2 to the 5th is 32, right? Yeah. 2, 4, okay, 32. And then power to a power, we're going to multiply, so we get a to the 30th and b to the 10th. And then 3 to the 5th would be 81 times 3, which is 243, right? Okay. So this expression would simplify to this. Any questions? Great. Okay. So all of this we did last year, and then this we did last semester. Do you guys remember this? Okay. So we're going to break down this radical. The 20 we're going to think of as 4 times 5. The x we can't do anything with. The y we don't need to because this is a square root, and we're taking half of that, so it's good. The z to the 7th you can think of as z to the 6th times z, so that we can take half of this one. So the square root of 4 is 2. It comes out. The 5 and the x stay under. We can take the square root of y to the 4th. We take half of that exponent, which is 2. We can take the square root of z to the 6th. We take half of that exponent, which is 3. Because square root is the same as what power? 1/2 power. This is the same thing as this. So that's why I'm saying it's things I can take half of. All right. And so this simplifies into this expression. There we go. Are we good? Excellent. All right. Now we'll pick up with some of the others later on, and we'll use those as warm-ups as we keep progressing through this unit. So our next unit, the one we just currently started, is on exponents and logarithms. So we're going to review the exponents because we did exponents last year, and I think you're going to remember it as we go back. So our review of exponents, our review is going to start with this. The first thing we're going to look at is solving equations where our variable is an exponent using like bases or a common base. Okay, so this is number 11 on the worksheet you picked up today. We're going to use this for some of our examples today. So number 11, we have 3 to the 5 minus 2x is equal to 81 to the x. Okay, so right now we have an equation where both sides are equal, and we want to solve for x. And x is the exponent, isn't it? So what we're going to do is we're going to rewrite this and this. We're going to take our bases and rewrite them as the same base. Is there any way to do that? Can I write 81 using a base of 3?
3 times
3 to the, a little bigger, 3 to the 4th. 81 is 3 to the 4th. So, did I change the value of this side of the equation at all? No, because 3 to the 4th is just a different way to write 81. They have the exact same value. So I haven't changed the value at all. I've just changed the form. So this could really look like this. Because a power to a power, what do I do with those exponents? Multiply them. So now I have 3 to the 5 minus 2x is equal to 3 to the 4x. The only way for this to equal this, if they have the same base, is if this exponent actually equals this exponent. Does that make sense? That would be the only way they could be equivalent. Is if this exponent equals that one. So we set the 5 minus 2x equal to the 4x and solve. Move the 2x over. Oops. Divide by 6. And we get x equals 5 6. Okay, so for my 9th graders, have you guys seen this before?
No, but it makes sense.
I'm not going to ask my 10th graders because I know you have, and I'm afraid some of you might say, no. All right, number 12. Here we go. This is another problem that we can use this method for solving on. So we have 1/6 raised to the 2x minus 1 and 36 to the x. Is there a common base for 1/6 and 36?
Yes, negative 1/6 to the negative 2.
Can I write these two, 1/6 and 36, using the same base?
Yeah.
What is it? 6. Yeah. Okay, now I just have to figure out what that is. How do I turn 6 into 1/6?
-1.
I raise it to the negative first.
Yeah.
So, did I change the value here? Do these have the exact same value? Yes, they have the exact same value. I've not changed the value of this side of my equation at all. I just changed the form. I changed the way it looked. I didn't change its value. We cannot change its value. Now, 36 is the same as 6 squared. So did I change the value of this side at all? No, I didn't change the value of either side. So they still should be equivalent, right? So now I have 6. I'm going to distribute that negative through. So I get negative 2x plus 1 is equal to 6 to the 2x. Once I have the exact same base, the only way these could be equivalent is if this exponent was equal to this exponent. So I'll set those equal and solve.
Yeah, I got 1 equals 0.
Okay, I wasn't going to show my work, but I will because you said that. To move this to the other side, you have to add. Okay? Okay, you should have gotten 1/4.
Okay, I did the same thing, Carter.
Really?
Yeah.
Okay, how are we feeling?
I was feeling good.
You okay? All right. We're going to do one more together. Yeah, this one's a little bit different. It kind of combines what we learned this year with what we learned last year. Common base. Let's look at these. 4 and 8. What's a common base?
4.
I think 2 would work a little easier. We could do 4, but you're going to get some fractional exponents. It's a little harder to work with. So we're going to rewrite 4 as 2 squared, and we'll rewrite 8 as 2 cubed. Okay, now, this one has a cubed root over it. How can I rewrite a cubed root? The cubed root is the same as what power? 1/3 power. So this could really be written as 2 squared raised to the 1/3. So this is 2 to the 2/3 is equal to 2 to the 6x plus 3. And now we're good. I subtracted 3. 3 is the same as 9/3. Okay. The one in the circle is call first, and then if that doesn't work, let me know. Alright. Okay, so now let's think about other things we learned in the exponential unit last year. Remember last year we were comparing linear functions with exponential functions, and linear functions had a constant rate of change, and exponential functions had a changing rate of change. Okay, so linear functions make a straight line, exponential functions made that little curve. All right, so this was our main form for an exponential. Okay, so this was our basic setup here. Y equals a times b to the x. And remember, a represented whatever our initial amount was, especially when it had to do with a word problem. So we're going to review word problems really quick because that's going to be your homework for tomorrow, whether we're here or not. Okay? And then b represents our base, our multiplier. Now, if our growth or decay is represented as a percentage, we'll write that percentage as a decimal every time, and we'll add or subtract that to 1. So if I said the population increased by 2% per year, our multiplier would be 1 plus 0.02. So you'll change that percentage to a decimal. If I said that my stock portfolio had been losing at a rate of 3% per day over the last month, it would be 1 minus 0.03, which would be 0.97. I think the rate of loss has been much greater than that, but we don't even look at it. We pretend like that money doesn't exist. it's okay. Doesn't matter until I'm 70 and I need it, right? Okay, so other things that could be here. If it said the bacteria doubled every hour, well, my multiplier would be 2. Or if we saw a word like triple, my multiplier would be 3. Or this was my class's favorite, the half-life problems.
Yeah, I love it.
Yeah, half-life, my multiplier would be a half. Now, x is going to represent the number of time periods. And that changes. If your percentage is per year, then the number of time periods would be the number of years. If we're talking about bacteria growing and it doubles every hour, then x would represent the number of hours. So x changes depending on your problem. Now, if this multiplier is greater than 1, then what we have is a situation of exponential growth. And if your multiplier is between 0 and 1, then we have exponential decay. All right, on that example sheet that you got first today, let's take a look at number 18 and let's remind ourselves about how we solve these problems. So number 18 reads, a population of 100 frogs decreases at an annual rate of 22%. How many frogs will there be in 5 years? In 10 years? How long will it take the frogs to reach half their original amount? So, first of all, we need to set up an equation which models this situation. It's an exponential, what kind of problem? Decay. So, what was my initial amount in this problem?
100 frogs.
100. 100 frogs. Times what?
1 minus 1.
1 minus. Good. 0.22. And this is to the x. And what does x represent in this problem? Years. Because it said it's an annual rate, so this would be the number of years. Okay, good. All right, so this is basically the setup.
X is that the number? Okay, X. No.
So you could write it like this, 0.78 to the x. All right, so is that a good model for this situation?
Yeah.
Yes, it is. All right, now we're supposed to determine the number of frogs that we'll have in 5 years. So what do we think we do with our model?
Plug in
Plug in
5.
We plug in 5 for x. Yep, so we get 100 times 0.78 to the 5th is approximately. Punch it in. See what you get. 28.8. Okay, now obviously, if this is a real life situation and we're talking about little froggies, we're not really going to have 28.8 frogs. I know that. But this is an estimation, so you might use 29 since it's decreasing. Sometime during the 5th year, we'll be down to 28, probably. All right. Now, you tried 10 years. Okay, so let's see what you got for this one. What did you get?
8.3 frogs.
8.3. Okay. So we'd probably say around 8 frogs, right? All right. So the last question. How long will it take the frogs to reach half their original amount? Well, how many were there originally? 100. So we want to know where this equals what? 50. Who has an idea on how to solve this equation. Okay, what you got, Carter?
We could put a minus 50 at the end.
Beautiful.
And then we find the 0.
Excellent. Okay, so he's using the method that we've been using on our polynomial functions to solve this exponential. Awesome. Now, we didn't know that last year, did we? We couldn't have done it that way last year. Go ahead and solve that real quick, see what you get, and then we'll talk about how did we approach it last year, because we didn't know to do this last year. What did we do? Please don't say you guessed.
Alright, to be honest.
I punched numbers into my calculator till I got something close.
That's what I did.
I know.
Don't do that.
Miss Wilby knows my secret.
I do.
2.78.
But I still got credits.
Okay, did you get 2.79? Approximately?
How do we supposed to solve that?
Okay, what Carter was saying is we graph it and we look at the zero.
Okay.
Oh, we
Second count.
do you calc it? I can't do that on this calculator.
Nope, but you can use the number solver on that. Not that I want to show you how.
Oh, I know how to do it. So just. But then, what would you put on this side?
I'm not telling you. What is on this side?
0.
50 is 0 and then x.
Wait, so 100.
Okay,
178.
which is why, because that calculator does all this for you and you really don't have to do anything other than breathe and punch, you will have to show work. Okay, so one way is to graph it and look at the zeros. Now, another way, and this is what we did last year, we were comparing linear functions with
Miss Willoughby,
exponential
I'm
functions.
confused how you went from the second step to the answer.
How do we go from here to here?
Yeah.
I graphed it and I looked at the intercept.
So how would you solve that without? Okay. So you'd have to grab
You
it.
you can enter this on that calculator and hit enter, and it will spit out this answer. That's what we just talked about.
I don't think it did.
Ooh. Okay. Maybe it won't. That'd be even better. All right. So last year we were studying linear functions and we were studying exponential functions. Why would that have been helpful? What can we do with this?
Nothing. Punch it in your calculator.
We could have set that y equal to 50 and y equal to 100 times 0.78x. And what this is going to do, this is exponential decay. And then y equals 50. And then what would we look at right here? Their intersection, right? So if this is y equals 50 and this is y equals 100 times 0.78 to the x, actually on your test I gave you the graph and you just had to read it. Because this would have been a little tricky. But that's what we did. We looked at the intersection of the two. And guess where it was? Right here at 2.79. Exactly. All right. So I kind of like our method now better, don't you? Yeah, it's a little quicker. What does our method do now? What is it doing?
We're basically
Translating the graph.
plugging
Yes.
it into the calculator.
All we're doing is we're taking this original graph and we are translating it down 50 units. So we're basically forcing this down to the x-axis and making that our x-axis. Did y'all know that's what we were doing all along? We've been translating. We've been translating. Okay. All right, let's, I'd like you to try. You try number 16. You set up the model for that equation and see what you get for 4 hours and 24 hours later. Number 16. Bacteria.
Did you really?
Okay, let's check it. Did you get 1 plus? Because this is increasing. So your multiplier is 1.035. Okay, your initial amount, 12 bacteria. And X represents the number of hours. Did you get all that from the reading? So if we did 4 hours later, we just plug in 4. That's approximately 13.77 bacteria. We would really round down. If this were an actual word problem, we'd say 13 bacteria. All right, 24. We get 27.4 bacteria. Okay? Is this grams of bacteria?
Yeah, it says grams.
Oh, then we could actually have it. Never mind. It's
Wait,
not
why
actual
would you
bacteria.
do-
Yeah.
A single bacteria.
All right. Now, what if this had not said every hour? What if it had said every 3 hours? What would we do differently?
You'd put it
Put a 1/3 right up there.
You'd put a 1/3 up here. We'd take all of these and divide them by 3. Thought I put it. Yeah, divide by 3. So this would be 8. Because if it happens 3 times, if it happens every 3 hours, wouldn't that be 8 times during a day?
Yes.
And then here we divide by 3, which would give us a rational exponent.
That's like common sense.
Okay, that's good common sense. All right, now number 14 takes us back to compound interest. Okay, do we remember compound interest? Okay, you remember disliking it. Okay, at least you remember it. I'll take that. All right, so here's our compound interest formula. The total amount is equal to the principal times 1 plus the rate divided by the number of times it's compounded raised to the number of times compounded times time in years. So P represents the principal. That's your initial investment. How much money did you initially invest? That's what principal means. Okay, R represents your rate, your interest rate written as a decimal. N represents the number of times your money, your interest is compounded each year. And T represents the time in years. Okay, so I think we all studied this last year, right?
Yes.
Okay, good. So, let's say it said it's compounded weekly. What would N be, guys?
52.
52, good. If it said it's compounded monthly,
12.
daily,
364.
Leap years?
5.
365.
Yeah. All right. We don't usually do 0.25, no. We'll just say 365.
What if we
Okay,
do 364 on a test, we get it wrong.
it would not be correct.
I feel like we should know how to do that.
Okay, so if you guys want to try those, these are the answers for A and B. Now C asks something very interesting.
Round down. It's
Huh?
364 and a fourth.
365 and 4.
It's 365 and a fourth.
Yeah, that's why you have leap years.
Yep, and the leap year takes care of that fourth every 4 years.
Um,
No, 5. All right. Okay, we'll move on. So, part C.
How many days are there in a year?
Part C says continuously. Now, continuously, you don't have to ask Siri. We all explained it to you. It's 365.
She's all over the place.
Yeah. Yeah. Apparently, she just doesn't understand
She
you.
gave me a decimal
Y'all
of
should break
how
up.
many years are in a year.
All right. So,
A year.
part C says continuously. And that's something we're going to talk about Thursday. Because tomorrow we're coming to school, and then Thursday we're coming to school. And on Thursday when we come to school, we're going to learn about a new number. It's the natural base. Our new number we're going to talk about is E.
I was thinking the same.
And I keep calling it number. It's your favorite number. Good. E is a number. That's all it is. It's a number. It's a weird number, but it's a number. Just like pi is a number. E is our new. It's a. That's actually part of my lesson. I don't want to give that away yet.
Wait, is that why E, it always comes up on my calculator a lot of times?
No, that's a capital E. We're talking lowercase e.
Make it lowercase e. Yes,
Oh,
yeah.
that.
No, that's a different E.
The one that's like.
I get this little bad boy. It's
I'm
like
talking about-
e to the power 10 to the power. Not that.
I'm so sorry. Anyone listening to this video, I'm so sorry. All right, so E is just a number. We're going to study that, and it is used in the compounding continuously formula. We have to move on. Okay, so number 17. I want to go over this one just because we haven't done a half-life yet. This is half-life, so obviously what's my multiplier? 1/2. Okay, what is the initial amount of radium in this problem, number 17? 8 grams. And it says the half-life is 1,620 years. So whatever our number of years, to figure out the number of half-life periods, we would have to divide by 1,620. Does that make sense? Okay, and that's how you would set up that problem. So you could determine the amount left after 3,000 years just by plugging in 3,000 there. And if you've already done that one, when you plug in the 3,000, you get 8 times 1/2 raised to the 3,000, divide by 1620. That's approximately 2.2 grams. Okay. So after 3,000 years, there's 2.2 grams remaining of that substance. Radioactive radium, yeah. Radioactive materials, their half-life is very large.
Wait, so a half-life is how long it takes?
How long it takes for half of the original amount of the substance to remain.
So is there any way?
Okay, now the last thing I'm going to talk about today are graphs of exponential functions. Now, I don't want you to write this down because we don't have enough time. I want you to watch, and then you can go home tonight and print out the slides. Okay? I will post this. You can go home tonight and print out the slides. All right, we learned how to graph exponentials last year. In my class, the very first thing you do is graph the asymptote. If there is no shift to the exponential, the asymptote is where? Okay, here we go. Right here, the x-axis. All right, so that's the first thing we're going to do is graph the asymptote. Okay, now we're going to think about this as the exponential function. We're starting at the origin. If I shift left 1, what's 2 to the negative first? 1/2. 2 to the 0, 1. 2 to the first, 2. 3 nice little points, nice little curve. Does it look like growth? Yeah, it's increasing from left to right. Okay, what would this do to this function? Shift it down. So the first thing I do is draw in my asymptote here at -5. The same process occurs though. All I do is I think about this being shifted down, so the origin, my new origin, is here. And so if I go left 1, I still go up 1/2. 2 to the 0 is 1. 2 to the first is 2. Draw in my graph. Yes. So all I did was shift it down. Okay? Now, what does this do? Shift it down. So that's the first thing we're going to do. Come over here. Shift it down. There's my asymptote. Now, what does this do?
Left 3.
Okay, we always do the opposite, so we're going left 3. So think of my new origin right here. So if I go left 1, up 1/2, 0, 1, 1, 2. Draw in my graph. So all I did was shift down 2 and left 3. Okay? Do y'all remember shifting around exponentials? Okay, now on this one, where is my asymptote?
2.
At 2. So that's the first thing I'm going to draw in. But do you notice that I've changed the base on this one?
I have.
Okay, I changed the base to 5. So we're going to go down 2, and what does this do?
Right.
1. But instead of going left 1 and up 1/2, we're going to go left 1 and up 1/5. Can't really tell any difference. 5 to the 0 is still 1, but 5 to the first is 5. So I'd go right 1 up 5. Very steep, isn't it? Okay? Now this one. What does this do? I can't answer that. Down 4. Okay. I need it every second. Hello? Sure. you can already see it. Doesn't this mean the same thing as this? But a negative with the x, isn't that a reflection over the y? Well, a negative x doesn't mean a reflection over the y? Oh no.
Everything I've learned.
I know.
Go on.
Okay. So, we can think of this as the decay, which if I did 1/3 to the -1, doesn't that flip it and make it 3? Or I can think of it like this, going right 1 and up 3, but then reflecting over. Doesn't that put me in the same spot? And you can think of it either way. Either way. All right, last one we're going to do has the negative out in front. And this is B on your worksheet if you want to do it with me. This is B on your worksheet at the bottom. Okay, where's the asymptote?
2.
Up 2. But this time, guys, the negative is in front. What does a negative in front of a function do to that function? Good. It causes a reflection over the x. So instead of this being exponential growth up here, it's going to get reflected down here. So instead of going left 1 up 1/3, I'm going to go left 1 down 1/3. Down 1. Down 3. There's my graph. Okay? You guys have a great rest of the day. Please keep in mind both assignments. You can find assignments for day 1 and day 2 online. Okay, so all of you that are not here today, your homework is the worksheet, pages 2 and 3 that are attached to my website. It'll say exponential, I think it says review. Do pages 2 and 3. They're attached to my website. Page 1 was what we used for notes today. So this is your homework for today. Your homework for tomorrow, even if we're not here, is out of your textbook, page 262, numbers 7 through 11, 15, 20 through 22, 27, and 28. Even if you didn't take your textbook home, you can still look this up online. And we'll see you on our very next school day.